Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Well, hello. Welcome back to another episode of the Reliability Matters podcast. Thanks for being here today. Today, we're going to kind of reprise a former topic, and that is thermal process management. We've talked about that before. We're going to talk about it again, but from a slightly different angle. My guest today is Miles Moreau. He's KIK Thermal's general manager, and he's been with KIK for nearly 3 decades. He draws his deep and rich experience from managing multiple business units across 4 continents. I guess he's not in Antarctica yet, spanning operations, field service, and sales and marketing channels. His experience is in thermal process management, and that's exactly what we're going to be talking about today. But as I mentioned, we're going to kind of take a different angle on it. We've discussed in the past a few times about a traditional view of profiling, and that is attaching a whole bunch of wires to a board and sending the wires and sometimes a recording device through an oven or through a wave soldering machine to capture all the thermal data points. Today we're going to be talking less about profiling a board, and we're going to talk about profiling a process. And if that's done correctly, the takeaway from that would be one might need to profile a board less often. And since we all know profiling a board is not a fun experience, it's a necessary but not a fun experience. You have to attach a lot of wires. You have to kind of know what you're doing. There's a lot of little tricks and tips to do that correctly. If we can reduce the amount of times we have to do that through a really insightful process management, thermal process management as opposed to board management, then life gets a little easier. And to make life a little easier, let's bring my guest, Miles Moreau, in. Thanks, Miles, for being my guest today.
Oh, thank you for inviting me. I'm excited about this discussion.
Yeah, me too. I was like talking about reflow, and as I said, probably ad nauseum many times on the show, it's often cited, whether accurate or inaccurate, it's often cited that every reliability problem in the field starts at the reflow process. So I'm not sure if that's true. I think there's plenty of processes to blame, but we'll go with that for the sake of this theme. When I think of a thermal profiler, as I said earlier, the first thing that comes to mind is attaching a bunch of wires to a board, and then the big argument is, what's the best method to attach a wire? And we've talked a lot on the show about don't use Kapton tape and don't do this, but do that, and best places to locate the wires and all of that. I generally don't think a lot about profiling a process. I view profiling as monitoring a process, but I guess everything in life is cause and effect. And so explain to me, I know that your company has done quite a bit of work about profiling a process, actually profiling an oven or a wave soldering machine to predict the results that one will get on a board. So tell me more about that process and explain the difference between profiling a board and profiling a process.
Sure. Yeah, and it does all start with profiling the board, because you have to get some type of measurement when you're setting up for a new assembly per se. And so you capture data, but the idea, if you look at the reflow process compared to other processes on the line, is it's kind of a situation where you're not at the same level of technology and capability with the other processes if you're only attaching wires, like you say, and capturing a single profile for an assembly. So what the idea being, and this is something that KIK innovated nearly over 40 years ago, actually. So that was kind of our expertise. Profiling became a necessity of attaching thermocouples to the board for our invention and concept of profiling the process or giving real-time data. So it's embedding thermocouples into the oven. So you're taking measurements at the board level of what's happening to the board. So when you do run that profile, that single profile, you're capturing the characteristics of the process as that board runs through. So we have thermocouples embedded into the oven down at board level from before the first heated zone through the cooling, and then you capture conveyor speed data by knowing what's happening on the conveyor motor continuously, and the product position. Where is the board in relation to the zones in the oven and these embedded sensors? And then what that creates is you're characterizing that process while you run your traditional thermocouples attached to the board profile. And just like you said, it is a pain. If you don't have everybody in your staff, engineers, technicians, operators trained at the same level and repeating everything the same way, your profiling results will end up different. So what this does is once you capture that good data from traditional profiling, you now turn it over to this system and technology of embedded sensors. And then it tells you during production in real time as each board exits what happened to that specific assembly during production. So now you're capturing the reflow profile, which is the process information, rather than just a one-time. It's every time a board exits the oven. So you're not just relying on set points. Is the oven in control for zone 1, 2, 3, 4, and so on? That's machine data. This is actually capturing process data during production.
So if I'm understanding you correctly, and I'm probably going to oversimplify it, but one of the first things that perhaps happens is a barcode gets scanned. So your system knows which board is entering an oven. I'm guessing. Is that part of
correct?
Okay. This is like a little mini Industry 4.0 all in one machine, right? So, and then there's multiple zones in an oven. Each one is monitored by a profiling system so that you know what the heater temperatures are at any given point in the oven. Or is there a sensor looking, maybe a contactless sensor looking at the board as the board travels through? It's detecting the temperature of a board. Are you looking at the oven specs or the result on the board in that case?
You're actually looking at the atmosphere temperature, the zone temperature at board level. So the difference being compared to a control thermocouple, which is up by the heater, the correlation between these sensors down at board level to that initial kind of programming profile that you run at the beginning is very closely related.
Right. So you have a X degrees at the heater, through prior profiling of the board, that results in X temperature at that location of a board based on conveyor speed and heater temperatures and things like that. So you're also tapping into the motors that run the conveyor. So you know how fast the conveyor is going, or do you measure the speed of a board going by a sensor?
No, it's actually sensing how fast the conveyor is going.
Okay. So you're interfacing with a lot of parameters of the machine. Does that mean that that the manufacturer of the machine installs your hardware, or is that a retrofit performed by your company or the customer or something like that?
Well, these systems in general, and there's different varieties of kind of what you would say automatic profiling systems. It is something that, like I said, 40 years ago is when we started this. It's kind of, we were a little bit before our time, kind of created this category, and now with Industry 4.0 and Smart Factory, it becomes a lot more relevant. The way you look at it, this is kind of one way I explain it, is for printing or for post-placement AOI, you have printing, you have SPI. So the best method to look at, did that paste print go down correctly, is 3D cameras. They're looking and lighting that paste print and saying, is that in the right position? Does it have the right volume? All this information is done through cameras. And then you have a kind of a golden data that says, here's what it should look like, and here's what this next board coming out of the printer looks like. Well, in that sense, you're adding material, and then you're inspecting it by taking a lot of pictures of it. In the reflow process, you're not adding material, you're adding heat. So what's the best way to capture that? You could say, well, the optimum would be to install a bunch of thermal cameras throughout the oven, so you have a full thermal image of the board as it goes through. Because of the technology and the cost, it's just not an effective way of doing that, because the cameras can't handle the temperatures inside the chamber, obviously, and they're expensive. So what we thought the most logical thing would be, well, you're talking temperature, then an array of thermocouples, kind of a mesh down at board level. So you do have the control thermocouple in the oven, but down at board level you have these array of thermocouples on each rail that kind of closely associate to the same air flow that is hitting the assembly as it goes through. So that's the kind of the best way I look at it. Is it's like, instead of these cameras, it's almost like tiny little cameras there, but it's actually thermocouples, because we're applying heat.
Right.
So we're not. That's the way we're inspecting the assembly as it goes through during production.
Right. If someone didn't engage in thermal process management, if they simply relied on profiling boards from time to time to check to make sure everything is still the way they think it is, what's the recommended frequency, or what's a common frequency of profiling boards, absent of this other technology?
Well, that's a good question, because based on our customers and the different manufacturing, from small to large, different types of assemblies, we get a large variety on what that frequency is. So some may be, well, we have a simple product. The oven doesn't change much, so we just profile once a week, or only if we have problems, then we'll go back and check the profile. To some of the customers that they're building for, may say, we want to know a lot more information about how you're building our boards. So we would like you to run it every shift that our boards are running, or once in the middle of the shift as well. So then it all becomes a matter of how willing you are, risk mitigation, I guess you could call it, is do I trust the oven? The ovens are very stable. They show that they're in control to these set points and the conveyor speed. So what does that mean to what's happening to the assembly? And that's the key where this automatic profiling comes in, is there are many conditions in the oven or in the process itself where the oven says green light, everything's fine, and it's controlling to the way, to the settings it needs to, but you are getting changes on the profile. And a spot check isn't going to always capture where those variations are. If you're trending towards going out of spec, if you end up going out of spec, you're not going to know until that next frequency when you run a profile.
Right. I guess you talk about risk mitigation. I guess one has to ask themselves, what's the maximum number of boards they want to scrap or rework? If if Murphy struck hard, the oven may have gone out of spec the board after, the board that was profiled, right? And then everything between then and the next board could be suspect. Now, the reason I asked about a frequency is if someone did institute a thermal process management strategy where they start profiling the oven or the wave solder machine. We'll talk about wave solder machines in a minute. But if they start profiling the oven and monitoring that, is it a reasonable expectation that would decrease the number of times one would want to profile a board? And would that you make the risk mitigation a little bit more, you can rest easier, when knowing that you're keeping an eye on the oven. I mean, obviously you can't profile every board that goes through. That would be impractical. It's like I'm in the cleaning business. We don't suggest we cleanliness test 100% of the boards, although some of our customers do. But
right.
It's all about risk efficiency, optimization, cost, risk mitigation. It's all thrown into the soup. So if someone does have the ability to profile the actual process, will that really result? Can one expect confidently to reduce the the frequency that one has to profile, or at best, can it even eliminate profiling again, unless there's a change made to the oven?
Well, the quick answer to your question is yes. It definitely, that as part of the value of the automation aspect of this is you are reducing the need to run the traditional profile through. You're capturing, so when you run that traditional profile, you're characterizing the entire process with a large amount of embedded sensors in there, which has been fine-tuned over the years of here's the amount of sensors you need. We could put in 60, 100 and put them all over the place, but at a certain point you're going beyond the need of monitoring the process. So once you've captured that characterization, then it just, like you said, unless there's something that's changed, maybe they did maintenance, then they had to replace the fans, or they took the rails out and had to do some major thing, then you might want to reestablish that base or that golden profile, make sure everything's back to the way it was. But otherwise, the system is it's telling you, hey, here's the next time you're going to have to run, because I can see the drift or the changes in the process in real time. Besides that, then it's really, if that's the only thing you're doing is running a traditional profile, then it's a little bit random as to, is once a week or once a day the correct amount. You don't know. You're just setting a frequency. Obviously, the more frequent, the better. But why do you go from once a week to once a day? Well, I get more information. Yeah, but why did you stop at once a day? Why didn't you go to once a shift? Because then it's not as efficient, and now you're stopping production all the time. So the ideal, really, at a very cost-effective way, is to automate that and capture that all the time. Then you do reduce the amount of profiles that you're running.
Okay, so I have a board A that's expected to be at X temperature at this point in the process. And as the board is going through the oven, something happens to a heater or something happens to a fan. And, partially through the reflow process, a system detects we're not there. We're over temp, we're under temp, we're too slow, we're too fast, whatever the case may be. What happens? Does it just say, hey, the board that just came out is didn't see the profile it expected to see? Does it stop the machine? Does it communicate outside of its footprint to some other mechanism to stop a process? What's the mechanism that happens when something is not as expected?
Well, just like any other kind of real-time inspection system, you can integrate it into your kind of even now it's more called the smart factory. If you integrate the system into the in-feed coming into the oven to a factory system, then you're able to detect, okay, I see that things are changing. I can throw up a warning either through the software, through visual, through actually stopping boards. And then what you're doing is, that board has already seen those changes. So at the end, when it exits, we can say, here's what those changes, how they impacted that board. Here's the profile it saw, the peak temperatures. Maybe because of whatever happened, the peak temperature dropped below what it should. So now that board is suspect to maybe having cold solder or some other defect. So you can flag that, and you also stop more boards from coming in until you can kind of look and then analyze what's happened during that time period. Because you have all those embedded sensors, not only do you have information about the board profile, but I have all these additional sensor sets down at board level that are saying, oh, here's what changed. You need to take a look at this zone. There was a big drop in this area. So it becomes a very good, like as you say, a thermal process management tool of mitigation of an issue, problems going on, reducing defects potentially by not allowing boards to continue going into that process that is no longer in control.
Yeah, you talk about one of the side effects or one of the results of not hitting your profile is potentially cold solder joints. I'll add one more. We did a study with Foresight Analytical Laboratories in Kokomo, Indiana, where we ran boards at the proper peak reflow temperature of 250 degrees C. Then we ran them at 240 degrees C peak temperature, 4%, 10 degrees, 4% off. No problem with solderability. Solder was fine. But we had increases in contamination. This was a no clean flux, not being cleaned. We had increases in contamination by over 600% in several measurable areas, and 200 or 300% in other areas, all because the peak reflow temperature was off by 4%. So there's a lot going on, not just solderability. You don't have to just do the old edge test, slam your board against on its side against a hard surface. And if components don't fall off, your profile was good. Right. There's a lot of other things that are going on that a lot of people don't realize, like increases in contamination, because the way no clean works is it relies on a certain profile, thermal profile, to burn off the activators and encapsulate the bad actors. And if that profile is off by just a little bit, everything looks good, but you have an ECM issue coming up.
And that's a perfect example of if you only go by traditional means of attaching wires, you have that sample and said everything's good, and you look at what are the things that can impact the quality or reliability of your product outside of what the machine, how the machine is performing, right? And the machine may be performing fine within your profile sample, but now during production you don't know. You see this in the cleaning, but you don't see it by taking a single sample. But you would if every board you see that drift is occurring. And that's where all this, which I think is really exciting, all this smart factory integration and artificial intelligence of relating all these different aspects of all the processes that can produce a defect. Because essentially you could end up, you're talking about 4%, and within the tolerances maybe of that process and that machine, if you stack those up from printing all the way through, you could look individually and say every machine said, yep, everything's fine, but a combination of just a small variation one way or another, and you end up with a defect. And that's where if you're missing a set of data along that manufacturing chain, then you can't perform that analysis, that artificial intelligence of, okay, how did this defect occur if all my equipment says everything's fine? Well, if you're not capturing all the data, your analysis is going to be flawed. So that's why, and then the reflow process has kind of been the last frontier of how do you do real-time inspection of what's going on there.
Yeah. What are the biggest challenges today? There's always challenges in our industry. Every industry can say that, I'm sure, but there, miniaturization and IoT, harsh environment. There's a lot of things going on in our business that allow us to kind of build. I think today at the closer to the edge of the envelope than the center, and then technology catches up, and then we come up with some new form factors that we don't know how to use, and then we fall off the cliff again, and then we come back on. And that's just kind of a wash, rinse, repeat historical matter. But what are the challenges that we see today that affect thermal management or affect reflow in general that maybe we didn't see before?
Well, I think a lot of the big challenges that we see become the packaging or the design of the assemblies. A lot of times they're not looking in turn. There's so many factors you have to take in just on the product itself. All the rules that you have for components and electronic design with wireless stuff, power, all of that going through. So then design for manufacturing comes in, and then you start to say, okay, now we have another set of rules for how this has to go through all these processes. And a lot of times the reflow process isn't taken into account. You have these very complex assemblies, especially say, let's take for example automotive, where you have this engine controller that has to have all these different style components and circuits on it to perform the way it needs to. But it has to have these big, huge connectors on them as well, and plug in inside a package that goes inside the engine chamber. So now you have these other requirements that make that assembly very complex. You have these huge, massive components, you have these small passives, and now you're trying to mitigate that on, okay, how do I run the board through the reflow oven? Which direction do I put it based on where the components are? Can I do 4 up or 6 up in a panel to get more efficiency on volume? Or because of that assembly design, I just can't do that because the connectors, I can't get them hot enough. Or if I get them hot enough, then the passives are going to be too hot, or a micro BGA is going to be too hot. So those complexities, and then you add in stuff like voiding. There's a lot of requirements by the end customers now to reduce the amount of voids. So that's the reflow process is a big part of that. Sometimes voids will grow during the reflow process. So how do you adapt either the paste materials or the profile to reduce that effect? And now they, even have reflow ovens with vacuum chambers to reduce the voids as well. Right. So all around that's sort of aspects of the requirements of these end products and the complexities of them really make it challenging to dial in the best setup for the process on reflow and then manage it during production. Because it's nice if you can really optimize, and the oven's all heated up and empty and everything. I run my NPI process development, get to the perfect recipe, and now I have to run a board going into the oven every 15 seconds. And so the oven characteristics are now different. The factory, the system of exhaust, when everything's running high volume, may change, impact things on the process. So all those things really make it a challenging manufacturing process that somewhat ignored, because I can run a profile through and I know what's going on, but there's a lot of things that happen outside of just the zone temperatures and the conveyor speed.
Sure. Let's talk about, let's switch gears a little bit. Whenever I hear thermal management, I think of, oven management. I think of profiling in a reflow oven. And it may come as a shock, but we're still using wave soldering machines. They haven't gone away. There's still a lot of wave soldering machines out there for through-hole components and connectors and even to some degree for surface mount. So let's talk about this thermal process management as applied to a wave soldering machine. In a wave soldering machine, there's three basic processes: you flux, you preheat, you solder. I don't think profiling has much to do with the fluxing stage, but certainly preheat and soldering are the two thermal processes that influence the outcome of a wave soldering process. What is different in the profiling of a wave solder process versus an oven process? Is it easier? Is it more complex? Is it the same but different? What are some of the challenges and some of the unique attributes of thermal process management in a wave solder machine?
I think it's much more challenging because there's still a certain art to setting up a wave solder machine. If you look at the different machines available out there, I think over the years the manufacturers have done a fantastic job of moving that art to more of a science. So there's more precision. But when you talk about as opposed to little small pads of paste and components, even though that those are very challenging when you put those through a reflow oven, you look at the wave soldering process, and it's a huge vat of liquid solder that's pumped up and creates a wave. So a very dynamic way of applying the solder, as opposed to the precision of a paste print and then going through the, adding the components and going through the oven. You have just a huge wave pushing the solder as the board goes through. So that alone and how that's managed, it makes it challenging. And then you add in the flux chemistry, and are you activating it properly through the preheat? If it's SMT and a mix of through hole, then controlling the topside temperature, so you have consistency of activating the flux, and then when it does go through the wave, proper soldering, but not doing any damage to the topside SMT components. It really creates a much more challenging atmosphere to dial in the process and control it.
Sure. Yeah, thank you for that. We're starting to run out of time, so I want to get through a few more questions before we hit the end of our show here. Your company talks about monitoring dwell time. I understand the concept of dwell time. It also talks about monitoring parallelism. You lost me. I've lost that game. I don't understand the concept of parallelism when it comes to monitoring through a soldering process. So maybe I'm the last person on earth to understand what that means, but go ahead and fill this ignorant mind with that knowledge, if you wouldn't mind.
Oh, yeah, sure. When we took on monitoring for wave soldering processes, because we had our profiling capability allowed the user to capture a profile, but the monitoring system, originally we just looked at the preheat, because that was simple. We could use the embedded thermocouples, know what's going on and how it's impacting, and then it stopped at the wave. So this past year we kind of worked on, the past 2 years up to the release this year, was to meet the customer's demands of, we need to have something in real time that's also capturing information about the wave other than just the temperature of the solder. And that was peak over the wave, So we had to add some sensors so we know what's happening to the profile through the wave, not just the preheat section, and then dwell and parallelism. So the dwell is, how long the board is dwelling through the wave. And knowing that, you can know you're trying to get a consistent temperature between the solder, the lead, and then the barrel that the lead's in. So you get a good intermetallic connection and good solder joint. So knowing the dwell time, you can manage that. And in real time, we've added additional sensors, and we're able to make a correlation between the sensor data and the dwell time to calculate an accurate dwell time during production. Now, the parallelism, it relates to dwell time and other factors as well, is the plane of the wave and how the assembly is going over it. So if you can imagine, if for some reason either the mechanical setup on the wave, or the way the pump is working, or there may be dross on one area of the pot, so the draw of the pump to push the wave up, then you create where the board surface is not parallel with the wave. So you may actually have part of the board going through the wave is not seeing the same depth and contact time as the other side of the board. So what we do is measure the dwell on each side of the board to determine, is that board going through parallel through the wave. So then, and the way that's kind of detected is if you did a spot sample, then what you're going to do is, well, did I see that during my test, was there a difference, and was it not parallel? Which is hard to do because a wave is so dynamic and moving. Your spot sample may just end up being fine, and during production, you're actually seeing a difference. So the idea being, if you can capture that in real time and you see a consistent change on one side, now you know there's something you need to address during production. Before it would be, I start to see defects on this one side of the board all the time, and now you have to go back and troubleshoot and say, there's a problem with the wave, the board's not going through parallel. That's why this happened, but that's after the fact. So by capturing it on each board, then you're able to mitigate that, stop boards from going in, and address the issue.
Excellent. I feel just a little bit smarter today. So thank you for filling me in on that. Our last question, because we are running out of time, is your company talks about SPC, of course, statistical process control. I think probably everyone knows that. And CPK. I don't think you're talking about California Pizza Kitchen. So tell me what CPK is. I'd love it if it was California Pizza Kitchen. I think talk about an application for thermal profile management, making a pizza. But what is CPK in the context you meant it to be in?
Well, using statistics to better have a better control of your process, the CPK is process capability. So it's looking at, you have a process, you have your spec limits and your control limits. So the spec limits are based on the materials, the type of oven you have, the assembly. I have to run within these limitations. On reflow, kind of the main driver, although there's a lot, are the materials. What does the paste need to go through? What kind of profile to achieve a good joint, and what are the limitations of the components? So those drive the spec limits, and then the control limits is where is my oven able to run and control that profile within those spec limits. Now, the deviation of that, the standard deviation, this is kind of getting a little nerdy into the statistical math, but how much that process varies and how close it is to the spec limit is kind of indication of the process capability, and that's what kind of the calculation of the CPK in simple terms is, here's how much my process is varying, and here is where it's varying within the process window. So in in older methods, you would have to run, say, 30 profiles, which if you're running once a day is a month, and then you have enough data that CPK value is actually telling you the trend of what's going to happen next. It's kind of a predictor of here's where my process capability is and here's where it's headed. And the reason why we kind of build that into the monitoring system or the real-time system is now it's 30 boards, not 30 days that you have a predictor in place. So now you can set a warning on your CPK if it starts to drop, which means you're going to have more defects per million. Then you can actually change something before you get to the point where it went outside your spec limit. So it's kind of a predictive mathematical tool to tell you here's where my process isn't trending and give you a warning ahead of time of a problem yet to come.
Yeah, that's the closest thing to a crystal ball that we can probably get. Miles Moreau, General Manager, Keck Thermal. Thank you so much for being my guest today. I really appreciate it. I wish we had more time. There's more questions that I have, but that's just an excuse for me to invite you back on the show again, and we can continue this conversation. Fair enough?
Oh, yeah, absolutely. Thank you. I think it's a nice opportunity, refreshing. Like you say, we always talk about the kind of the tips and best practices of profiling. But if you take that to the next level, which is done across the rest of the factory, and do that in real time, it brings a whole nother aspect to, it makes the term profiling not so bad anymore.
That's right. Yes, I agree. All right, wonderful. For those of you who are listening or watching this show, if you go to the show notes, if you're on YouTube, just look down below the video, hit the click more or show more link, and it'll provide contact information for Miles. And for those of you that are listening, just go to your podcast site and look at the show notes, and we'll have Miles' contact information in case you have more questions. If he's whet your appetite for knowledge, feel free to respond to him or email him, and I'm sure he'll be more than happy to get the answer or find out where the answer is buried and dig it up for you. Right, Miles?
Absolutely.
Okay, sounds great. Well, thanks everyone for joining us. I appreciate you being here. And Miles, thank you so much for being my guest today. We'll talk soon.
All right. Thank you, Mike.
Thanks for listening or watching the Reliability Matters podcast. Be sure to subscribe to the podcast on your favorite podcast app, such as Apple Podcasts, Google Podcasts, Spotify, and so many more. Also, be sure to check out my other podcasts, including the Concept to Creation podcast, where I feature conversations with entrepreneurs within the electronic assembly space, and the Innovations in Technology podcast, where we discuss innovative products within our industry. All three shows are also available in video format. Check out the Reliability Matters or Concept to Creation or Innovations in Technology podcasts on YouTube. Just search the show's name and you can find all three shows. Or go to MikeConrad.com, that's Conrad with a K. All three shows also appear there. Again, thanks for being part of my podcast family. I appreciate you being here. Until next time, stay safe, stay healthy, and stay happy. And of course, keep doing it right. See you again soon.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.